ever jumped out of a plane? Okay, maybe not literally, but just imagining it. The wind rushing past the ground, seeming miles away. You're experiencing a whole bunch of forces at work, and guess what? Those same forces are what get your morning coffee to your table. Today we're doing a deep dive into the world of forces, those pushes and pulls that shape our reality, guided by your collection of physics lecture slides. Let's break it down.
What's fascinating is that we navigate a world governed by forces every single day without even realizing it.
It's like a secret code that explains how everything moves and interacts, right? But before we can crack that code, we've got to understand the basics. What exactly is a force? It's more than just a nudge, isn't it?
Exactly. Think of force as any interaction that changes an object's motion. Picture that classic physics demonstration. A hand pushing a ball. Simple, right? But that simple push reveals the essence of a force.
Well, we measure these forces in a unit called newtons, right? I always think of Sir Isaac Newton. Wasn't he the guy with the apple and gravity?
That's him. Born back in 1643, Newton basically wrote the book on forces in motion, literally. But before we get to his famous laws, let's talk about the different types of forces.
Okay, let's unpack this. What kind of forces are we talking about here?
We can group them into two main categories. Contact forces, those requiring touch, and non-contact forces, the ones that act from a distance. Let's start with contact forces. Imagine trying to slide a heavy box across a rough floor. That resistance you feel, that's friction. A contact force working against you.
Ugh, I know that feeling all too well. It's the enemy of every furniture rearrangement project.
Exactly. Now picture a suspension bridge. It's massive cable stretching across the span. The force in those stretched cables, that's tension, another type of contact force. These contact forces are literally what hold things together and allow them to move.
So then non-contact forces would be those that seem a little more mysterious, like that weird feeling when two magnets pull towards each other without even touching.
You got it. Magnets are a great example of non-contact forces at work. And what about the force that keeps you from floating off into space right now? That's gravity, the ultimate invisible force.
Gravity definitely feels more familiar than, say, whatever force makes magnets work. But you mentioned there are even more fundamental forces.
Absolutely. In fact, there are four fundamental forces that govern everything in the universe. We've talked about gravity, but there's also the electromagnetic force, the strong force, and the weak force.
Wow. Okay, that's a lot of forces. It's amazing to think that everything we see and experience is a result of these forces interacting with each other.
It really is. And to understand how they interact, we need to delve into the brilliant mind of Sir Isaac Newton and his three laws of motion.
All right, Newton's laws, let's do it. I'm ready for some groundbreaking physics.
His first law, often called the law of inertia, states that an object at rest stays at rest, and an object in motion stays in motion at a constant speed and in a straight line, unless acted upon by a net force. Imagine a hockey puck gliding across the ice. It would keep going forever if it weren't for friction and air resistance.
So objects are kind of lazy. They just want to keep doing what they're doing unless something forces them to change.
That's a great way to put it. And speaking of forcing a change, this principle of inertia is why you feel a jolt when a car brakes suddenly.
Oh, I've totally felt that. It's like my body wants to keep moving forward even though the car is stopped.
That's inertia in action, and it's the reason seatbelts are so important.
Wait, so seatbelts are actually a safety harness for our inertia?
Exactly. In a crash, a seatbelt applies a force that counteracts your body's natural tendency to keep moving forward, which can be a lifesaver.
That's incredible. It's physics saving lives every day. Okay, I'm ready for Newton's second law. Hit me with it.
Gravity. It's the force we all know, the one that keeps our feet on the ground. But it's so much more than that. It's a fundamental force of attraction between any two objects that have mass.
So me, you, that coffee mug over there, we're all pulling on each other with this invisible gravitational force. That's wild.
It is. And it's always an attraction, never a repulsion. Gravity is always trying to bring things together.
Okay, but if that's true, why don't we see objects being pulled towards each other? Like, I don't feel myself being drawn toward that bookshelf across the room.
That's a question that puzzled scientists for centuries. The answer lies in the two key factors that determine the strength of gravity: mass and distance.
Okay, so the more massive an object, the stronger its gravitational pull.
Oh.
That makes sense. Like, the Earth is huge, so its gravity is what keeps us from floating away.
Exactly. And the farther apart two objects are, the weaker their gravitational attraction. So while you are gravitationally attracted to that bookshelf, the force is minuscule compared to the Earth's massive pull on you.
So it's like a cosmic game of tug-of-war, and the Earth is winning by a landslide because of its sheer size.
That's a great way to think about it. And it's not just about keeping our feet on the ground. Gravity is responsible for so much more. The moon orbiting the Earth, the tides ebbing and flowing, even the very structure of galaxies across the universe.
Speaking of the moon's orbit, wasn't there a scientist way before Newton who was already thinking about these things? Galileo, right?
Yes, Galilei, born in the late 16th century, was way ahead of his time. He challenged the traditional view of gravity, which held that heavier objects fall faster than lighter ones.
Wait, heavier objects don't fall faster. That seems counterintuitive.
It does, but Galileo's experiments showed that in a vacuum where there's no air resistance, a feather and a bowling ball would fall at the exact same rate.
So it's the air that slows down a feather more than a bowling ball.
Precisely.
Uh,
Galileo's work paved the way for Newton's law of universal gravitation, which put a mathematical framework around this invisible force.
okay, so Galileo set the stage, and Newton came in with the mic drop. The law of universal gravitation. What does this law actually tell us?
It states that every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers.
Whoa, that sounds intense, like something out of Star Trek.
It's definitely a mouthful,
Okay,
but essentially it means that the more massive the objects, the stronger the gravitational attraction between them. And the closer they are, the stronger the pull.
So even two small objects exert a gravitational force on each other. It's just that the force is so incredibly tiny, it's basically unnoticeable, right?
Exactly. But don't let the small scale fool you. This law explains why planets orbit stars, why galaxies cluster together, why black holes warp the fabric of space-time. It's the driving force behind the universe as we know it.
It's amazing to think about. So we've talked about different types of forces and Newton's laws. Earlier you mentioned force diagrams as a way to visualize how forces interact. Can we dig into those a bit?
Absolutely. Force diagrams are incredibly helpful tools for analyzing the forces acting on an object. They give us a visual roadmap to understand motion. Imagine a book resting on a table.
Okay, got the book, got the table. What forces are at play here?
It's like a cosmic game of tug-of-war where each force gets to pull on an object. The net force tells us who's winning or if it's a tie.
Okay, I'm picturing a bunch of tiny forces, each with their own little rope, pulling on, say, an apple hanging from a tree. So how do we calculate who wins this force tug of war?
We add up all the forces acting on the object.
Yeah.
If two forces are acting the same direction, we add them together. If they're pulling in opposite directions, we subtract.
So in our force diagram, if we had a big arrow pointing down for gravity and a smaller arrow pointing up for air resistance, we'd subtract the air resistance from gravity to find the net force.
Exactly. And that net force would tell us the direction the apple is accelerating.
Which in this case would be down towards the ground because gravity is stronger than air resistance.
Right. But what happens if the forces are perfectly balanced? What if the net force is zero?
Wouldn't that mean the object isn't moving at all?
Not necessarily. Remember Newton's first law. An object at rest stays at rest, and an object in motion stays in motion at a constant speed and in a straight line, unless acted upon by a net force.
So if the net force is zero, an object could be at rest or moving at a constant speed. It's like that hockey puck gliding across the frictionless ice. It would just keep going.
You got it. It's all about balance. Now, this might seem a little abstract, so let's bring it back to something we were discussing earlier, gravity. Remember that question you asked about why we don't feel ourselves being pulled towards large buildings or even other people?
Yes, it's been bugging me this whole time. If gravity is pulling everything together, shouldn't I feel a little tug towards, say, that stack of physics textbooks over there?
You are. But the force is so tiny, you'd never notice it. It all comes back to mass and distance. The Earth is so massive compared to those textbooks, its gravitational pull completely overshadows everything else.
So it's like trying to have a whisper heard in a hurricane. The Earth's gravity is the hurricane, and all those other tiny gravitational forces are just whispers getting drowned out.
That's a great analogy, and it highlights a crucial point. Understanding forces isn't just about knowing the definitions. It's about understanding their relative strengths and how they interact in the real world.
It's like realizing that physics isn't just something you learn in a textbook. It's literally happening all around us all the time. This deep dive has been eye-opening. I feel like I'm seeing the world with new eyes.
That's the beauty of physics. It's a way of decoding the universe, of understanding the fundamental forces that govern everything from the smallest atom to the largest galaxy.
Well said. This has been quite the journey through the world of forces, from those we can see to those that are invisibly shaping our universe. We've learned about Newton's lost force diagrams, net forces, and so much more. But perhaps the biggest takeaway is that the world is far more dynamic and interconnected than we often realize. Every time you take a step, open a door, simply sit still, remember. Forces are at play, silently orchestrating the incredible ballet of motion that makes up our reality. So the next time you're sipping your coffee, take a moment to appreciate the invisible forces at work, from the friction that keeps your mug from slipping to the gravity that keeps you firmly planted on the ground. Keep exploring, keep questioning, and keep your eyes open to the wonders of the physical world. Until next time, this has been The Deep Dive, your shortcut to being well informed.